projects which are sponsored by KCSST. All the participants can post their queries in the chat box during the event and later by the end session. The questions will be discussed in Q&A question and answer part. About you, sir.
Okay, Bhargav, am I audible?
Yes, sir, you are audible.
Uh, Very good evening to all. Okay, I'll present my screen. Wait. Bhargav, can you see this PPT?
Yes, sir, it's visible.
So this is a workshop of AutoCAD. So in this workshop, in 2 days, I'm going to speak on introduction to design of electrical machines and design of again two electrical machines. We are seeing design of transformer, and after designing the transformer, it's drawing using AutoCAD software. Then we'll again go for design of DC machine. Again, once we obtain the data from the design of DC machines, from the data we'll go for drawing the DC machine in AutoCAD. Okay. Then computer aided design and drafting, that is CADD. What is this computer aided design and drafting? We'll see in further. Then lastly, we'll see the introduction to AutoCAD. So first we'll see the design of these transformer and DC machine. After designing uh, this one, we'll go for introducing the AutoCAD. How the AutoCAD software is downloaded and installed, and how the basic things are in AutoCAD. Okay, in today's sessions, we'll see these things. Tomorrow, what we do, and today's sessions will go for only designing of the transformer and DC machines. Okay, once the data is obtained from the designing of transformer and DC machines, from the data, we'll draw those transformer and DC machine diagram in AutoCAD. That is in the next session, that is tomorrow section, using AutoCAD. So let's start with the design of what is design in engineering. So engineering design is the process of devising a system, component or process to meet desired needs. Okay, so we are designing the system or component, okay, to meet the design need. What are the design needs? Sometimes for a systems we want a higher efficiency, we want a low cost product. Okay, so these are the needs. According to these needs, we need to design the system or component or any product. Okay, so basically what it is a decision making process. What is design? It is a decision making process. What decision here? Whether the product is for higher efficiency, or the product is for lower cost, or the product is compact or not. These are the decision making. Based on these one, okay, we use some engineering science and mathematics which are applied to convert the resources optimally to meet a stated object. What is the stated object here? Again, what the product with maybe a higher efficiency we want, the product with a low cost we want, or the product with less volume we want. These are the object here. Okay, to achieve this object, okay, we are utilizing the resources we have optimally. Optimally means what here? With a less cost investing in the resources, we are we are utilizing the resources to meet the stated object. This is what design in engineering. So this is a basic definition of design in engineering. So what is design of electrical machines? Since we are talking about the electrical machines, so throughout the sessions, what we're doing, we are designing the electrical machines. So we have taken two examples, that is a transformer and a DC machine. Okay, so we are design a transformer. Again, transformers, we are talking about the power transformer, and we're talking about the DC machine, that is a DC generator. Okay, that is of higher capacity. Okay, we're talking about these transformer and DC machine design. Okay, once we obtain the data from this design, data means what here? Physical parameters. Okay, what is the size of the machine? Okay, those things. Okay, once we obtain these data of the design, by using those data, okay, we draw a structure of a transformer or a DC machine in AutoCAD. Now, what is design of electrical machines? So it is a process of selecting proper materials and to resolve the conflict for space between magnetic, conducting, and insulating materials so as to produce a cheap and highly efficient machine. So what is the design of electrical machines here? So it is what processing is selecting a proper materials. So what are the materials we are used in manufacturing a DC machine or transformer? For example, in transformer we have a core, and the core is made up of what? It is a silicon steel. Okay, that material that is called a magnetic material. And in a transformer we have windings, and windings are nothing but a conductors, and the conductors are made up of aluminum, copper, or these materials. So these materials, insulation is there. What kind of insulation we are providing here? It depends upon the temperature. Okay, the class A, class B, class C. Okay, so selecting these materials, okay, and resolve the conflict for the space between. Okay, so there is a magnetic material, conducting material, and insulating material. Okay, so has to produce a machine which has got la- which is cheap and highly efficient. That is a design of electrical machine. What is the main aim of the design here? The main aim of design is to obtain completely the dimension of all parts of the machine. Okay, complete dimension of all parts. Again, for example, transformer. So in a transformer, what are the main parts? We have a core, we have a windings here. Okay, so uh, the aim of the design is what? Obtaining the dimension of core. What is the core height? What is the core length? What is the core width? Okay, these things. Then come again in transformer we have a windings. Windings are nothing but a conductors. Conductors are wound in a to form a number of turns. That is nothing but a coils. Okay, what is the size of the conductor? How many turns are there in a transformer? LV winding or HV winding? LV means low voltage winding, and HV means high voltage winding. How many number of turns are there in these windings? Okay, and what is the size of the conductors we use for making low voltage winding, for making high voltage winding? So determining these complete dimension, that is the main aim of the design. The design should be carried out based on the given specification. How we start the design? How we start the design? So if there is a customer or some company is there, they want uh, uh, a transformer or a machine. Okay, so they have to provide specification. What rating of transformer they want? What rating of DC machine they want? What rating of synchronous machine they want? What rating of induction machine they want? Which uh, which electrical apparatus is required. Okay, they need to provide the specification. For example, transformer rating is what? It is always in kVA. How much kVA transformer they want? Like, 1000 kVA, 2000 kVA, 1 MVA. kVA means kilovolt ampere. 1 MVA, 1 megavolt ampere. Okay, specification. A transformer specifications are many things. One is power, then voltage ratio. Okay, what is the low voltage winding voltage they want? High voltage winding, how much they want? Okay, what is the frequency of operation? How much temperature rise? Okay, that is also specification. Okay, how much losses? The losses should be in this range only. What is the efficiency? How much is the power factor? Okay, these are all specifications they need to provide. Based on these specifications, we start the design of the electrical apparatus. Like electrical apparatus means again transformer, DC machine, AC machine, or these things. Okay. Again, what? Using the available materials economically. Again, materials is what? Again, conducting, magnetic, insulating. Okay, these are the materials. They need to utilize these materials to manufacture the electrical apparatus. Okay. Again, to achieve the following, to design, okay, the given product apparatus. Okay, for what thing we have to design? For a lower cost, for a lower weight, reduced size, better operating performance. Okay, based on these are nothing but a object here. So some customer want a product means, and I'm talking about electrical machines. They want, for example, a transformer. They want a transformer of so and so specification with less amount in lower cost. So this is the main objective, keeping this thing in mind, that is a lower cost product they want, we need to design a transformer. Again, some customer or some industrial company, they want a transformer which is of lower weight. This is the objective. So keeping lower weight in mind, we need to design a transformer. Okay. Then some company, they want a reduced size, compact size transformers. Okay. Again, keeping this in mind, we need to design. Again, better operating performance. So these are nothing but the objective. Okay. Keeping these in mind, we need to design a electrical apparatus. Now, electrical design engineer. Okay, so this session is all about. This is helpful for electrical design engineer because electrical designer designs the electrical machines. So especially we're talking about electrical machines. So design engineer should be quite familiar with the following aspects of electrical engineering. Okay, he has to know these all things: various electrical materials. Okay, again I told various electrical materials are nothing but we're talking about matting materials, insulating materials, conducting material. You should have a thorough knowledge of these materials, their properties, their market price. Okay, the strength of those materials. Okay, there are many factors. Okay, electrical characteristics, what are the temperature level and all that. So he should be familiar with these various electrical materials. Now, second one, properties of magnetic and electrical circuits. Okay, again we are talking about electrical machine print. Obviously, there is a magnetic material and there is a electrical material. Okay, magnetic materials are nothing but they are used for making the cores. When transformer, it is called as a core. Okay, magnetic material. That core will carry the flux from one winding to another winding. Okay, that is called a magnetic material. Okay, and we're talking rotating machines. Magnetic materials are nothing but armature, stator, poles. These are all called the magnetic materials. And electrical circuits or electrical material means what here? This is nothing but a conductors or windings. Okay, these conductors or windings are present in transformers as well as in rotating machines. And transformers, that is nothing but for windings, and in rotating machines these are also windings in armature, and there is a windings in stator also, poles, field windings. Okay, so he should be familiar with these things. Now he also knows what are the laws, governing laws. Okay, see, there are certain rules, Indian standard we need to follow for manufacturing. Okay, or for designing the electrical apparatus. Okay, for example, there is a standard ratings of electrical apparatus only we can produce. Okay, so we need to follow those standards. Okay, so for in India there is a frequency of 50 hertz. So we have to design the electrical apparatus for this 50 hertz only. We can't design the apparatus more than 50 hertz. So we need to follow a certain governing laws of in anywhere. In India, it is Indian standards. Okay, so we need to follow those laws. The laws of electromagnetic induction. What are the laws of electromagnetic inductions? That is the basic things you already know. That is Faraday's laws. Faraday's first law, second law. Okay. So how the EMF will get induced. Okay. Whenever changing magnetic flux links with a conductor or a coil, an EMF will get induced across that coil. These are the laws. We should also familiar with these laws. Okay. Which material will can induce how much amount of flux in the another coil. So he should know about these laws of electromagnetic induction. Now, calculation of magnetic circuits. And what are magnetic circuits? These are nothing but a cores or armatures. Transformer, it is a core, it is called as core. Rotating machine, it is called as armature poles. Okay. So calculation of magnetic circuits. Calculation of magnetic circuits means what? Again, we're talking about the dimensions. Okay. What is the length of the core, height of the core, or those things. Okay. How much flux density it can carry. Okay, then in rotating machines we have a field coils. Okay, and field coils will carry a field current. How much amount of field current should be there to produce the sufficient amount of flux to carry in a rotating machines? So we need to calculate again dimensions of the poles, dimensions of the armature, stator. So these are nothing but a calculation of magnetic circuit. We should know the calculation part of the magnetic circuits. The designer also should quite familiar with the construction of various types of electrical machines and their behavior under working conditions. Okay, once we manufacture, he should also know how this machine will behave in certain operating conditions. Okay, so the designer should be quite familiar with these aspects of electrical engineering. Specifications. As I said, to design any electrical apparatus, the first thing is what we need a detailed specifications. Okay, detailed specifications. So the main electrical apparatus are, we know, transformers, rotating machine, that is a DC machine, and AC machine. Again, in AC machines we have a synchronous machine and induction machine. Okay, now specifications. Firstly, transfer specification is according to Indian standard, it is 2026-1962 and 1180-1964. Okay, these are according to Indian standards. We need to follow the transformer specification. And what are the main specification of a transformers? This is nothing but a input data for a designing of the transformer. Okay, so what are the data? What are the specification required for design of a transformer? So power output in kVA or MVA. Okay, so always transformers. Its power rating is always given in kilovolt ampere or megavolt ampere. Okay, so first thing we need this one. Then voltage ratio on load, on no load condition. Okay, voltage ratio. Voltage ratio means what here? Uh, Secondary voltage by primary voltage or primary voltage by secondary voltage. This is a voltage ratio. Okay. How much voltage they want in the LV winding, how much voltage they want in the HV winding. Okay. That thing has to be specified. Then frequency of a transfer. Obviously, in that is 50 hertz. Okay. And the number of phase. Okay. So a transformer design means what? If it is a three-phase transformer, number of phases here. Okay, if it is a single phase, so there are two phase. If it is three phase, there are three phase. Okay, then class of transformer. Again, transformers are divided into depending upon the power rating or power output. It is classified as power transformer and distribution transformer. So distribution transformer, you can see that by the side of the road, that is of smaller rating. It is of 25 kVA, 50, 100 kVA, 200 kVA. Okay, so these are all nothing but a distribution transformer. And power transformers are, it is 1000 kVA, 1 MVA, 5 MVA. These are all power transformers. Okay. So again, they have to specify whether they want a distribution transformer or a power transformer. Then LV and HV windings connection. So if it is a three phase, okay, how the LV winding they want, whether they want LV winding connection in delta or in star. As for HV winding also, what they want, HV winding in star connection or in delta connection. Because in three phase we connect the winding in two ways. That is, we connect the windings in delta or in star. Okay, so here sometimes both the windings they want in stars, sometimes both the windings they want in delta, sometimes one is delta, one is star. Okay, so they have to specify the winding connections also. Then percentage of tappings. So on the transformers, on power transformers, they also have to specify the tappings. Okay, tappings mean by varying these are the tappings provided on the turns, number of turns, that is on the windings. It may be on secondary or it may be on primary. So by varying the tappings, we can change the voltage. We can vary the voltage. That is nothing but the tappings. Sometimes all power transformers will come with tappings. It is maybe manually or automatically. Okay, so why the tappings are required here? So the if the load is connected to the secondary, okay, that is the load is connected to the HV winding. Okay, uh, always the load on the power transformer is always varying. So secondary voltage, that is on HV voltage winding, is also varying. So we need to maintain a constant voltage. So for that purpose, the tappings are provided. If the voltage is falling, so we need to set the tappings as the voltage will start increasing and it will get to stable. Sometimes the tappings are automatic. Okay, it will we have to set the voltage change. So according to that one, the tappings are adjusted and the voltage is maintained stable. Or in some case it is manual. So by hand we need to set the tappings, set the voltage. Okay, so they have to specify also the percentage of tappings. Then phasor group reference for three-phase transformer. Okay, phasor group. Again, phasor group is what? Delta LV. Delta LV, phasor group. So at what angle they want delta connections, at what angle they want star connection, the phase group. They want like RYB, BRY. So these are nothing but a phase group. Okay, they have to also specify. Then maximum temperature. So the transformer is manufactured. So the maximum temperature rise in the transformer. Okay, so we need to design a transformer so it can sustain this maximum temperature. So they have to specify. For example, they want the maximum temperature rise for 150 degrees Celsius. So we need to design a transformer for this maximum temperature 150 degrees Celsius. Okay, if the temperature goes beyond this 150 degrees Celsius, it may damage the certain parts of the transformer. So the carefully we have to design a transformer so that its maximum temperature rise should be go up to 150 degrees Celsius. At that temperature also the transformer will work normally. So these are the specification of a transformer. Then coming to the rotating machines according to Indian standard 4722 1968. So according to Indian standard, so what are the specification of a direct machines? They are DC machines. So we need to follow the Indian standard for the specification of a rotating machines. Then first, we're talking about the direct current machine, that is a DC machines. Okay. First thing is what they want, a DC generator or a DC motor. That should be specified. Then type of field excitation, and for DC machines we required a field winding. Okay, the type of field excitation for whether it is a shunt field they want or series field or cumulative differential, these are the type of field excitation they have to specify that one. Then rated output power. Okay, what should be the power of a DC machine? Then rated voltage, speed, how much speed they want. If it is a DC motor, they have to specify the speed. Okay, uh, then type of enclosure. Okay, that is a body of a transport. Type of enclosure. What kind of enclosure they want. Then type of duty. See here, we have to design a DC machine that depending upon the application. Okay, by what load that these DC machines are carrying. Again, the loads may be a short time, intermittent, continuous. Okay, if DC machine is working for short time. Okay, short times, that is with certain time period. Okay, it will on and will get off. Okay, for short time. So for this kind of duties we need to design a DC machine. So they have to specify that what type of duty the DC machine is carrying, intermittent, continuous. Then field excitation voltage. Okay, so how much field excitation voltage there is required, they have to specify that one. Then maximum temperature rise, again this is also, so what temperature or DC machine can sustain, that is a maximum temperature, and they have to specify these things. So these are the specification of a DC machine and transformers. These are also nothing but the input data for designing the machines. Next one is alternating machine. Again, what for alternating machines, whether they want a generator or a motor, they want a synchronous generator or synchronous motor, or they want an induction generator, there is or induction motor. Then type, whether they want a induction machine or a synchronous machine. Then rated output, a rated voltage, frequency, what speed they want, how many number of phases, then connection of winding. Again, it is a three-phase alternator, okay, or induction machines. Again, connection of winding, that is star delta. The type of rotor winding, okay. If it is for AC, it is a rotor winding, maybe a squirrel cage, slip ring for induction motor. Again, the type of duty, what type of duty the alternating machines are carrying. Again, the type of enclosure, type of cooling, and if it is a synchronous machine, exciter voltage. Okay, for a synchronous machines we need a DC excitation voltage. How much excitation voltage is required, they have to specify that one. Then lastly, maximum temperature rise. Okay, that these are the specifications of electrical machines. Okay, based on these specifications, based on these main data. Okay, uh, and properly assumes values of specific loading, the process of design is initiated. Okay, so these are nothing but a main data, specifications are taken as the main input data, and certain things we need to assume before proceeding to the design. Okay, for example, specific loading. So as I said, for electrical machines, uh, we have a magnetic circuit, we have electrical circuit, and for a magnetic circuits we have a specific loading, and for electrical circuit we have a specific electrical loading. Okay, so we need to assume the values of the specific loadings. Okay, so while designing the transformers or DC machines, I will say what is the value of specific loadings for a magnetic materials or for a electrical materials. Okay, once we assume certain data and the main input data, the process of design is initiated. The process of design is initiated. The design data for various parts of machines are then used to calculate the performance. Once we design the various parts of a machine, lastly we need to check the performance of these parts here. If we design a core, okay, if we design a core of a transformer, so we need to check the performance of the core. Theoretically we need to check here, okay, whether the flux carrying by this core, it is not saturated, it is not heating the core. Okay, these are all things we need to check. This is nothing but a performance. Okay, if the performance are in the is in the range, okay, then the design part is said to be okay. The performance, okay, of the parts, okay, is going above certain limits, then again we need to redesign the parts. Okay, again we have to redesign the parts, again by doing certain values of specific loadings, or certain many things we need to assume. Again we have to change the assumed things, again we have to design the parts, again we have to check the performance of the various parts. The performance are well uh, in the limited range, then the design of the part is said to be okay. Okay, the performance thus calculated should satisfy the service conditions specified for the machines. Okay, it has to satisfy the service condition. Okay, as I said, for electrical machines there is a specific loadings. Specific loadings are nothing but specific magnetic loading, specific electrical loading. So specific magnetic loading, what is the specific magnetic loading? It is for the magnetic metals. So what is specific magnetic loading? So specific magnetic loading, it is nothing but it is a total flux per unit area, total flux per unit area over the surface of armature periphery, over the surface of armature periphery, and is denoted by BAB, B average, also known as average flux density. Okay, total flux over total flux. Uh, so this is we're talking about the rotating machines total flux per unit area over the surface of armature periphery. There is a armature, there is a rotor. On the rotor surface, what is the total flux? Total flux, okay, on the armature periphery. That is nothing but a specific magnetic loading. So for the specific magnetic loading, we need to assume the certain specific magnetic loading for a magnetic metal and start designing. Okay, and the specific electric loading, these are comes for a winding here. And what is the specific electrical loading? So it is defined as the number of armature conductors. Okay, so here we are talking about the windings. Windings are nothing but what? It contains a conductor cells. How many numbers of conductors are there? Okay, we are talking about electrical loading machines. So we have a armature there. Armature contains a armature conductors. Okay, so number of armature conductors per meter of armature periphery at the air gap. Okay, so what is this air gap? We always, for loading machines, there is air gap between a stator and rotor. Okay, so here number of armature conductors per meter of armature periphery. Armature periphery per meter. How many armature conductors are there? That is nothing but specific electrical loading. Okay, so this is given by Q. IA, that is nothing but a armature current. ZA is the number of conductors. Pi D. D is the diameter of the armature. Okay, this is specific electrical loading. So what value of specific magnetic loading and what value of specific electrical loading we need to assume? Okay, see here, we can't take a higher value of specific magnetic loading, so we can't take lower value of specific electrical loading. So it will affect the design. How it will affect? See here. So in rotating machines, power output. Okay, we have rotating machines. Power output is directly proportional to the following quantities. D square L. What is this D? D is the diameter of the armature. So you take any rotating machines, for example, DC machine rotor, that is nothing but a armature. So diameter of the armature, D square into L, length of the armature. Okay, so power output depends upon these dimensions, or depends upon the dimension and the length. Then speed of the rotor, power output is also depends upon the speed of the rotor. Then it will also depend upon specific magnetic loading, specific electrical loading. Okay, so the choice of increased value of specific loadings, if you take higher value of specific loadings, okay, so these gives rise to higher total losses, increased no load losses, poorer power factor, and higher temperature rise. So if you take a higher value of specific loadings for magnetic and electric, so this will increase total losses. Also, it will increase no load current, will give less poor power factor, and there is a higher temperature rise. So, so we can't even choose the lower value. If you choose the lower value, this will increase the size of the machine. This will increase the size of the parts of the machine. Okay, so the if you design by taking lower values, so that if the design values gives the larger volume of the parts, so we can't even choose the lower value of specific loading, we can't even choose the higher value of specific loading. So there should be compromise is to be made between these conflicting factors. Okay, so suitable values are assigned to the specific magnetic and electrical loading. So suitable means where, so the losses are also not much, even the size of the machine is also not much. There should be some compromise we need to make. Okay, then by choosing these assumptions of specific magnetic loading and specific electrical loading, we'll start designing the machine. We'll see general design procedure. What is the general design procedure here? So, firstly, what, based on the given specification of the machine, choose proper materials. Okay, again, what, conducting, insulating, and magnetic. Okay, so what are the specification of the machine they are given? According to that, we need to choose the proper materials. Again, choosing of proper methods, it depends upon the objective function. What kind of machine they want. They want a lower cost, lower volume, lower. Depending on that one also, we need to choose the materials for conducting, insulating, and matting. Okay. Next, basic design parameters. Again, next thing is what, we need to assume specific magnetic loading, specific electrical loading. As I said, as I told, we can't take the higher values of specific magnetic loading and specific electrical loading, nor we can't take the lower values of these loadings here. So proper value of specific magnetic and electrical loading we have to assume. We have to assume. Then once we assume the specifications in these specific loadings, design procedure is initiated. Okay, then start calculating the various dimensions of magnetic and electrical circuit. Okay, using the various design equations. Okay, using design equations, start calculating the dimensions for magnetic and electrical circuits. Dimensions, again, what, physical dimension we're talking, size of the core, size of the windings, and all that. Then based on the calculated dimensions, performance of the machine under no load and loaded condition is predetermined. Once we obtain the dimensions of magnetic and electrical circuits, okay, we need to again check the performance of the machines. How the machine will work. Theoretically, I'm talking. Theoretically, we need to check the performance of the machine under no load. On no load, how the performance of the machine is there. On full load, that is loaded condition, how the performance of the machine is there. The performance is okay, that is in a quiet range, okay, then the design is said to be okay. Again, we need to also check the temperature rise. Okay, for a design of the dimensions of the various parts, what temperature rise is taking place after designing these dimensions. If the temperature rise is also in a given range, then the design of the parts is said to be okay. Okay, then after that one, the calculated performance of the machine is compared with the customer requirements. Once we design, once we check the performance, everything is okay. Next thing is what? The performance of the machine is compared with the customer's requirement. Customer's requirement. Okay. If the performance is not satisfactory, okay, if the customer is not satisfactory, the designer has to modify the basic assumptions of the design parameters so as to bring the final decision closer to the objective. Okay, we need to design if the customer requirement is satisfied. Once it is satisfied, okay, the designed data, okay, is take for manufacturing of the machine. This is the general design procedure. Now we'll start with a design of transformer. A design of transformer. So what we are doing, once we obtain the design parameters, that is nothing but a dimensions of various parts, by using those dimensions, we draw the structure of transformer in AutoCAD. Okay. So before that, to draw the structure of diagram of transformer, we want a data. Okay, we want a dimensions. So for a dimensions, okay, so we are designing a transformer. This is a role of an electrical design engineer. Firstly, he has to design the electrical machine. Okay, if it is okay, then the customer is satisfied. It satisfies the requirement. Next thing is what, drawing of that electrical machine using those data. Okay, then we'll go for the manufacturing. Okay. uh, so basic thing about the transformer is what here, you know that transformer is of two types: single phase transformer, three phase transformer. Okay. And transformer consists of a magnetic core, okay, that is also said to be magnetic frame, and a windings or a coils, primary and secondary coils. Okay. And you can see always primary and secondary coils are wound on each other. Here we are not talking about the not primary and secondary. We will talk in low voltage winding and high voltage winding. Always high voltage winding is wound on low voltage winding. So far what you have seen, for explanation purpose, you have seen that primary winding is wound on different leg, and secondary winding is wound on different leg. Okay, but actually in practical these windings are wound on each other. Okay, secondary winding or HV winding is wound on uh, LV winding, that is a low voltage winding. So you can see from the figure, it is a single phase transformer, it is a three phase transformer. So left side, okay, you can see this is a core. Okay, you can see this vertical line, this is a vertical core, and the horizontal, this is called as a yoke. Okay, this is core, this is yoke. Okay, so there are in single phase there are two cores, that is nothing but two limbs or legs. Okay, and at the top and bottom it is nothing but a, it is called as yoke. Okay, always the windings are wound on the core. Always windings are wound on the core. On the core, first always LV winding is wound, low voltage winding is wound. Upon the low voltage winding, HV winding is wound. Okay, this is for single phase transformer. Again, transformer is of two types: core type and shell type. Okay, shell type windings are letting for shell type it is three limb transformer, and the winding in shell type is wound on the central limb always. Central limb. Okay, remember. In shell type always windings are wound on a central limb, but in core type windings are wound on each leg. Okay, if it is for three phase transformer, windings are wound on three legs. Okay, you can see for a three phase transformer we have three cores. Okay, and at the top and bottom it is called as yoke. Okay, and also we have three phase means there is a three windings. Okay, three LV windings and three HV windings, and these windings later they are connected in a different fashion. Maybe it is in star or it is in delta. So always remember the HV winding is wound on the LV winding. Aim of design of transformer. What is the aim of design of transformer? Okay, so what is the aim? So getting the dimensions of various parts, getting the physical dimensions of various parts. That is the aim of a design of transformer. To obtain the following informations regarding its various circuits. using the given specifications and selecting the proper materials for various parts. This is nothing but a aim of a design of transformer. First thing is what main dimension of a matrix circuit, that is core, yoke, and window. Okay, so the what is the aim? The aim is to design core, yoke, and window. What is this window? So you can see the space you can see between core, between yoke, that is nothing but a window. Okay, the space available at the center, that is nothing but a window. So main dimension of matrix circuit, so that is one getting the dimension of core. Again, what length of core, width of core, height of core. Again, same thing for yoke and window. What is the size of the window? Okay. Then what design details of low and high voltage winding. So low voltage winding dimensions. Okay, what size of conductor they are used for making low voltage winding. Okay, we need to calculate the size of the conductor used for low voltage and high voltage winding. Okay, so the main aim is to design or getting the dimensions of windings low and high voltage. Then once we design every part of a transformer, the next thing is what? Performance characteristics. We need to check each part performance. Okay. If the performance are in the range. Okay. Again, the design is said to be okay. We'll go for next step. Okay. That is manufacturing. Then, lastly, design details of the tank. So again, what uh, design of core, yoke, and window. We also see the design of the tank. Tank is nothing but what? Tank is nothing but in the tank we place this core and windings. That is nothing but a tank. Always this core and windings are surrounded by the tank. Okay, and the tank maybe it consists of insulating material, that is oil, or maybe it is a dry type transformer. Okay, so that's the material tank. So tank houses the its core and windings. So we need to design core, yoke, window, windings, low voltage and high voltage. Then check the performance of these parts. Then design details of the tank. Design details of the tank. Uh, in order to determine the above design information, designer needs the following. Again, as I said, so design all these things. First thing is the designer, electrical engineering design. They need detailed specification of a transformer, limiting values of performance characteristics. Limiting values mean how much losses they want, how much temperature rise they want. These are the limiting values of performance. How much no load current they want, how much copper losses, how much no load losses, how much temperature rise, maximum temperature they want. These are the limiting values. Okay, they we required based on these limiting values and for the given specification data, we design the transformer. So again, for designing the transformer, we required various design equations. Okay. Again, as I told, we also look for what is the choice of specific magnetic loading, current density, okay, window space factor. So as I told, there is a space between core and yoke, that is a window. Or how much is the window space factor we need to choose. Again, that depends upon the rating of the transformer. Okay. Factor KF for step to core type. Okay. Core may be a square type, two step, three step. Okay. And for that we need to choose a factor KI. So while designing the transformer, I will tell you the factor KI. What is this factor KI? Then information regarding the level insulation at different places. So we are talking about the transformer design means there are windings, there are magnetic circuits. Okay, we require an insulation between between the parts. Okay, so again, the level of insulation depends upon the level of temperature. What level of temperature is this transformer is withstanding? Based on that one, we need to choose the type of insulations. There is an insulation between core and LV winding. There is an insulation between LV and HV winding. There is a insulations between the windings also, between layers of the windings. Okay, so what level of insulation is required? Yeah, information regarding materials available for various parts. We require this one. So one, calculate, after doing all these things, calculated performance is compared with the normal limiting values of a performance again the performance of the design transformer is satisfactory, then go for further process, that is for manufacturing. If it is not satisfactory, again there is certain changes we need to make. Again, we need to design the transformer to achieve the better performance. Okay. Now we design a transformer, that is nothing but optimal design. Okay. uh, to make one of the following quantities as minimum, that is nothing but the optimal design. Optimal design means what? So we're designing for total volume, total weight, total cost, total losses. So based on these things, we are designing a transformer. Okay, by keeping these things in mind, if we want to reduce the total value of a transfer. So this is the objective function. Okay, so we need to design a transfer to get the optimal solution, best result. That is nothing but we are designing a transfer for a less volume. Okay, so there is also a total weight. So we need to design a transfer for a less weight. We have to design a transfer for less cost. These are nothing but optimal design objective functions. These are the specifications we need to queue for a transformer. Okay, these are act as a input data for designing process. Now we'll start the design of transformer. Okay, so I have referred this problem from electrical machine design book, that is a BK Mehta. So here uh, they have gone in detailed design of every parts. Okay, once we obtain the data, that is dimensions for every parts, using those dimensions we start drawing the transformer structure in AutoCAD. So here what one example I have taken for designing of a transformer. So design a transformer having the following specifications. What are the things we need to design for a transformer? Magnetic frame, that is core and yoke. We need to design LV binding, HV binding, then check its performance characteristics. Then lastly, design the tank. Tank is nothing but which will house us the core and bindings. Okay. So the specification, for example, the customer want a transformer of this specification. They want 1000 kVA and high voltage is 6600 and low voltage is 440. Okay, this is nothing but a voltage ratio, high voltage by low voltage, and frequency 50 hertz. Three phase they want, and they want a delta star, high voltage in delta, low voltage in star phase connection, and they want the transformer as core type, not cell type. They want core type. So it is a three phase. For a core type, we have a three legs, three cores. Okay, then power class. Okay, it says it is 1000 kVA. They want transformer, power transformer they want, and what type of cooling they are using. It is oil immersed. Oil immersed means that a tank, transformer tank contains a oil. Okay, and it contains the bindings and core. So this whole structure, that is a core and binding, is immersed in oil. This oil is nothing but this is insulating oil, and also it is served as a cooling for that one. Okay, then self-cooled. Again, the transformer, like they want the self-cooled transformer, or sometimes they want forced cooling. They use some exhaust fans and all that. That is nothing but a forced cooling. So here they want a self-cooling transformer, and the temperature rise not to exceed 50 degrees Celsius. So keeping these things in mind, we start designing the transformer. Again, they are saying total loss not to exceed 1.5% of the rated output. Okay, what is the rated output? It is 1000 kVA. Okay, so total loss should not exceed 1.5% of the rated output, and no load current. Okay, as I said, if there is no load on a transformer, there is some current flowing in a transformer. That current is nothing but a no load current. Okay, this no load current is what? It is a vector sum of magnetizing component and core component. Okay, so due to magnetic material and due to core material, there is some current flow in your transformer. That current is nothing but a no load current, and they want this no load current to be within 1% of the rated current. What is the rated current of 1% of that one? And how to check the rated current? That is power divided by voltage. So from that we can get the rated current. So no load current should be 1% of the rated current. Then percentage impedance to be within 6 to 7%. Okay, percentage impedance. So if there are windings are nothing but what conductors. So every conductors has got certain uh, resistance and inductance. So how much percentage of resistance and inductance they want in the winding? That is 6 to 7%. So keeping these things in mind, we proceed for designing a transformer. First thing, we'll design a magnetic frame. We design a magnetic frame. In order to design a magnetic frame based on the given specifications, okay, following design equations are needed. So first thing is what to design a magnetic frame. First thing is what EMF per ton, electromotive force per ton. The windings are there. So windings are nothing but a coils. So coils are nothing but a turns. How many turns are there for making a winding? So for 1 ton, how much EMF it is? So the equation for that one is what ET equal to K root KVA by KVA per phase. Okay, or it is given by ET equal to 4.44 F BM AI. What is F? That is a frequency. BM is maximum flux density. AI is what? It is the uh, area of the core. Okay. Then uh, this k as et equal to k root kVA per phase. This k is a factor and whose value depends upon the type of transformer. You can see the table given below is what how the value of k is to be chosen. It depends upon the type of transformer. Okay, if it is a three-phase core type, so the factor k should be chosen between zero point 0.6 to 0.65. Between these, in the range, we need to choose the value of k for three-phase core type. Okay, and if it is a three-phase core type distribution, if it is a shell type, single phase or single phase shell, there are different values of factor k is there. So we are this problem. This transformer is what this is a power transformer core type. So we'll choose a factor k between zero point 0.6 to 0.65. Then cross-sectional area of the core. AI is nothing but a cross-section area of the core. Core is what on which we owned a binding, LV binding, and on LV binding we owned a HO binding. Okay, the core it is there. The area of that core is given by A equal to K D square. K D square. What is this D? Small d. Small d is what? This is the width of the core. Width of the core. And what is this K? This K depends upon the uh, what type of core, whether it is a stepped core, square core, how many stepped core, depend upon that one. Okay, uh, if it is a square type of core, the core structure, if you see the core from the top, it is a square one, then the factor k is chosen as 0.45. Okay, and if it is a cruciform, it is a cruciform structure, like it is like a circle type. It is the factor of k chosen as 0.56. If the core is three stepped, so it is zero point 0.6. If the core is four stepped, it is 0.62. Now you can see here given there is a figure. If you see the core from the top view, this is a three stepped core. So he can see how the three step. This is called a three step. If it is two step, there are two steps only. Okay, if it is a square, so there is core is square here. So here we are taking a three step core for this core type of transformer and we start designing. Okay, the output of a transformer is given by Q. So this is the equation 3.33 of PM kW delta AI AW volt ampere. Okay, so window area or the AW is window area, it is given by L into capital D minus D. Okay, by using these equations, okay, we'll start the design of a transformer. For three-phase core type power transfer factor. Okay, uh, K is what value you chosen for three-phase. You can see this K E equal to K. K we have to choose between zero point 0.6 to 0.65. Okay, so we are choosing 0.62. Okay, 0.62. And what type of material we are using for magnetic frame? So here we are using cold rolled grain oriented silicon steel. There is also hot rolled grain oriented silicon steel. But for making the magnetic frame of this material, So we are using cold rolled grain oriented silicon steel. So why there are different types? It depends upon the flux carrying capacity of this material. Okay, there is flux carrying capacity of cold rolled is different, hot rolled is different. So we are choosing for making matic frame, we are choosing cold rolled grain oriented silicon steel. So while designing a transformer, many things we need to assume. So assumption is what? It again it depends upon the performance. Lastly, the performance of the all parts it should be in the normal range. So according to that, we need to assume all the values. So here we are assuming the matic frame material is cold rolled grain oriented silicon steel, and maximum flux density in the core we are assuming 1.5 Tesla. 1.5 Tesla, you can see. So how the maximum flux density we are assuming, since we are using hot rolled silicon steel for a power transformer, we have to use maximum flux density between 1.2 to 1.4 Tesla. Okay, so we are taking 1.5 Tesla. Okay, so uh, here it is 1.2 to 1.4, so we are taking nearer to 1.5. Okay, so if the flux density is more, uh, the flux density is more, flux carrying ability is more, so we can reduce the volume of the transformer. So for that purpose, keeping that in mind, so we are taking flux density near to 1.5. Okay, so first one is what? Hot rolled, second one is cold rolled grain oriented silicon steel. So for power transformer it is 1.5 to 1.7 Tesla. Okay, and the core type we are using three step. You can see how to design the three steps here. So you can see the smaller step. You can see the smaller step is what? It is 0.42 of capital T. What is this capital T? This is the diameter of the core circle. Okay, that D. Okay, so smaller step is 0.42 of D, and then the second step is zero point 0.7 of D, and the third step is zero point 0.9 of D. Okay, so this is how we design a three-stepped core. Then window space factor for this core to power transfer KW we choose 0.34. Okay, and how we have chosen this 0.34? This is the formula. Okay, if the transformer rating is 1000 kV, we have to use KW equal to 12 divided by 30 plus kV. Okay, voltage of a HV winding we need to use. So for supporting voltage of HV winding, so we get KW equal to 0.34. Okay, window space factor. And average current density we are choosing 2.2 into 10 raised to 6 ampere per meter square. And again, how we are choosing this current density? It is a power transformers. We have to choose between 2.3 to 3.5 ampere per meter millimeter square. Okay, so we are choosing 2.5 10 raised to 6 ampere per meter square. Okay, then window proportion. So it is proportion is what? L by D minus D equal to 3.6. So again we need to assume the window proportion equal to 3.6. Okay, because what for this power transformer 1000 kVA we need to assume the window proportion. Proportion is nothing but width of the window, height of the window. Okay, it is what between 2.5 to 4 we need to assume. So we are assuming 3.6. Okay, the iron factor, since we are using cold rolled grain oriented silicon steel, and for that material the iron factor is 0.92. 0.92. Okay, then gross area, that is a yoke area. Gross yoke area. Okay, so yoke area, okay, that is AY. So it is taken as always 1.15 of gross core area AC. Okay, then density of steel we are taking 7.55 into 10 raised to 3 kg per meter cube. Kg per meter cube density of steel we have taken. Okay, so these are the data and equations are used for carrying out the design of the transformer. Okay, first thing is what? EMF per turn. So what value of K we have chosen? It is zero point 0.6. So it equal to 0.62 root. What is the rating of power transfer? It is 1000 divided by 3. So EMF per turn we are getting 11.3 volt. This is 11.3 volt is for 1 turn. Okay. Then net cross section area of the core. Net cross section area of the core, that is AI. So what is the equation we have? Uh, I can see from this one output of the power transformer we can calculate AI. Okay, we know the output of the power transformer frequency, flux density, window space factor, current density. Okay, so using that equation, so we can calculate net cross section area of the core. We are getting is 0.034 meter square. Okay, we can convert this into mm. So this will be 340 millimeter square. Okay, that is net cross section area of the core. Then diameter of the circumcircle round the core. This one you can see this is a three-step core. There is a circle around this core, three-step core. The diameter of that one, the diameter of that one, the diameter of that one is what? Uh, it is 0.24 meter. Okay, 0.24 meter. Then modified net cross sectional area of core. Okay, modified net cross sectional area of core is zero point 0.6 into 0.24 square. So there is a formula that is k into d square. Okay, you can see. So we have a formula. You can say AI equal to k d square. So area modified net cross sectional area of the core is what? 0.0346 meter square. Okay, the amended value of EMF per turn. Okay, so it is 11.5 when you substitute UT, frequency, flux density and all that, so it is 11.5. Then window area from the output equations, we can get window area as 0.36 meter square, and we know that ratio that is L into D minus D is 0.136. Okay. And we also know that we assumed the performance of the proportion of the window is L divided by D minus D equal to 3.6. Okay, so from these two equations, we design uh, capital D and L. What is this capital D? Capital D is nothing but what? Center to center distance between the core. And L is what? Length of the core. And overall length of the rope, that is a W. So from all these equations, so we design for the dimensions of the core. So you can see from this figure, so it is center to center distance between, that is nothing but a D of a core. Okay, small d is what? Width of the core. L is what? Length of the core. W is what? You can see this is the length of the yoke. Okay, length of the yoke, and this small PW, that is nothing but a width of the window. Width of the window. Now you can see HY, that is the height of the yoke, and width of the yoke. So height of the yoke we are getting zero point 0.2 meter, and width of the yoke we are getting 0.216 meter. So here I have written all these things. Okay. Uh, Lastly, I will show these all in the table. So the design of a frame of a power transformer, that is a magnetic circuit, that is nothing but a core and yoke. Okay. So what we got here, small d equal to 0.24 meter. Okay. Then length of a core is zero point 0.7 meter. Then center to center distance between the core, that is capital D, is zero point 0.4 meter. And length of the yoke we are getting 1.076. Okay, then height of the yoke is zero point 0.2 meter. Okay, next thing is what, once we have designed the dimensions for the magnetic frame, that is nothing but core and yoke. Okay, check the performance of the magnetic frame. Iron losses, what percentage of iron loss, how much is the iron losses is taking place, you have to check one. So by doing all these things, what we got, the total iron losses is what? 1990 watts. 1990 watts. Okay, And this, if we compare this total iron losses with the total rating, so this is nothing but what, it is approximately 0.2% of the total output. So they are told it should be in the range of 1%, so we are getting 0.2%. Therefore this is satisfactory, and the dimensions for the magnetic frame is okay. Okay, now no load current. So, so if you check the calculate the no load current for this one, so it is 0.42%. Okay, in the custom, it is in the range, the performance range only. It is below the value of the performance range. Therefore, again, the dimensions which were designed for magnetic frame is said to be okay. Next, design of low voltage winding. Okay, low voltage winding. For low voltage winding, the number of turns per phase T2 equal to T2. So how we got this number of turns per phase? So you can see number of turns per phase in LV winding, that is T2 equal to LV winding, that is voltage 440 divided by root 3. Okay, phase voltage. Okay, divided by this uh, uh, divided by 11.5, that is equal to 22. So number of turns per phase is LV winding. Okay, uh, number of turns per phase T2 equal to 22. We got what is the current density for LV? We are choosing it is 2.3, 2.3 ampere per millimeter square. Okay, so therefore current per phase. So we got cross sectional area of a conductor is 571 millimeter square. So how we are arranging this LV winding, you can see. Since there are 22 turns, these will be arranged 11 axially and 2 radially. 11 axially means what here? There are 22 turns. Okay, so 11 axially and 2 radially. Okay, that means vertically we are taking 11 coils, and radially we are taking 2 coils. Okay, the conductor size is too big and thus standard into 12 parallel strands, each with 47.6 millimeter square area. Okay, now we know that length of the core is 70 centimeter. Okay, axial space for winding. Okay, it is always taken 56. That is 20% we have to leave for insulations. If 20% of 70 is good, it is 56. Okay. Now what we are arranging the LB turns in 11 axially and 2 radially. How it will look like? So you can see. So this is what. Uh, this is for one. This is for one turn here. This is for one coil. Okay. So Excel space available for one turn is what? 56 divided by 11. So 11 is what number of turns in one layer. Okay. So it is 5.1 centimeter. Okay. So then Excel space available for one strand. So they are taking 12 parallel strands. Fine. So 12 parallel strands of one turn are arranged 3 axially and 4 radially. Okay. So 5.1 divided by 3, it is 1.7 centimeter. 1.7 centimeter. Okay. So finally what we obtain, we obtain is, so here thus amended section area of LV conductor, size of a strand with double cotton cover. Okay. On the LV winding we are placing a cotton cover as an insulation, and the size of that LV winding, okay, for one strand, it is 16.4 mm into 3.4 mm. 16.4 into 3.4 mm. Okay. Now what next thing? So this is what uh, this is for one coil. This is for, you can see from this figure, this is for one coil. 16.4 we are placing in a vertical and 3.4 in a horizontal way, and we are wounding the LV body in one layer. In one layer, how many conductors are there? It is in 4. Total it is 8. Now if you to calculate this one, so it is so here it is vertically 12, and here it is 8. Okay, so this is how we wound the LV winding. Okay. Now radial adjustment of the winding. What is the radial width of the winding? Okay, So finally, what we get radial width of the binding. See, you can see uh, uh, inside diameter. Radial width of the binding, it is 29 mm, 2.9 centimeter. Radial width, if you see from the center of the core in a horizontal direction, that is nothing but a radial width. And vertical means that is an axial length. Okay. Now, uh, outer inner diameter of insulating cylinder is 25 centimeter. Okay, so we know that circumscribing circle diameter is 24 centimeter or 240 mm. Okay, so on that circle, on that core, we are using a oil duct between core and LV former. Between a core and LV former, we are using a oil duct of 0.5 centimeter. Okay, so why this oil duct? This is nothing but for cooling purpose of the windings. Then after this oil duct, we are placing the insulating cylinder. We are placing the insulating cylinder. Okay, between the core and LV winding of 0.3 centimeter. Width of the insulating cylinder is what? 0.3 centimeter. Outer diameter of insulating cylinder is 25.6. Now again what we are placing a oil duct between insulating cylinder and LV winding 0.5 centimeter. Now the inner diameter of LV winding we are getting is 26.6 and outer diameter of LV winding we are getting is 32.4 centimeter and radial width of LV winding we are getting is 2.9 centimeter. 2.9 centimeter. So radial width of LV winding we are getting is 2.9 centimeter. Fine. Now again, once we design LV winding, check its performance. So for checking its performance, what we getting? Total copper loss in LV winding is 3718 watt. Again, this is in a given range of a performance, therefore it is said to be satisfactory. Now design of high voltage winding. Okay, and for design of high voltage winding, we can see how many turns are there for HV winding, so we can calculate from this formula. Okay, so we know that transformer ratio, that is N1 by N2 equal to V1 by V2. By using that one we can calculate the turns for HV winding. So for HV winding we are getting 572 turns. Okay, and how we are arranging these turns? uh, so complete winding of each phase is sectionalized into 15 coils. 13 coils of 40 tons each and two ends of coils of 26 tons each. Okay. Uh, so finally, I will tell you the size of the conductor for this one. Okay. Uh, Size of the conductor for this one we are choosing 7.9 mm into 2.9 mm. 7.9 mm into 2.9 mm. And how the conductor we are placing 7.9 in a vertical way and 2.9 in a horizontal way, and we are wounding on one over the other. And how many layers are there? So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 layers. Okay, there are 12 layers. Fine. And how we are arranging? We are arranging uh, 4 conductors axially and 10 radially. So you can say 10 radially and 4 axially. And there are how many turns are there? There are 40 turns. And there are 40 turns. And you can see from this data we are also getting the radial width of the coil also. It is 2.9. It is also for H1 it is 2.9 centimeter. Okay. Then axial arrangement of the winding. Axial arrangement. So if we arrange this axial space for 15 coils, okay, how many coils it is for H winding? It is 15 coils. Okay, uh, 15 coils are there. Okay, and how we are arranging for this one? Axially 15 coils. Okay, and what is the size of this one coil? It is, you can see it is 31.6. Okay, so we are taking 3.16 in centimeter. Okay, So it is 47.4, okay, of one coil, and between these coils we are using 6 mm spacers, okay. So it is 8.4. So total axle length of the coil we are getting 70, okay, 70 centimeter or 700 mm, okay. And radial adjustment, so this is what external adjustment of the HV winding, radial adjustment of the HV winding. So for radial adjustment of the HV winding, so you can see, for radial width of the HV winding we are getting 2.9 centimeter only, it is 29 mm. And what are the things are there between LV and HV winding? Again, there are insulation and oil ducts, okay. So you can see oil duct between HV former and HV winding is zero point 0.5, okay. And thickness of HV insulating cylinder 0.6. So these are all data we are using for drawing the transformer in AutoCAD. So lastly, I have tabulated all these dimensions, okay. From that dimensions we'll draw the transformer in AutoCAD. Again, what after determining the axle length and radial width of the HV winding, okay, performance of the winding, okay. Again, find the total copper losses. The total copper losses are in the given range, so we are getting 5,817 watt, okay. And no load current, so it is given 0.42%. So what is the no load current getting, and the losses? What is the total losses we are getting? Uh, Total copper losses in both the windings you are getting is both the windings, that is LV and H winding, 9,535 watts. Okay. So if you compare with this rating of the power transformer, it is 5%. Okay. Hence the design of the LV winding H winding is okay. Okay. The dimensions are taken for manufacturing purpose. Fine. Then efficiency. So you can check the efficiency. It is 98.8, 98.9. So this is also okay. Okay. The maximum efficiency is getting 98.97. So higher efficiency. Regulation we are checking. Okay. So regulation, voltage regulation and power factor we are checking. Per unit impedance, per unit reactance, resistance. Okay. So these are all we are taking per unit values, PU values. So these are what, after calculating the dimensions, we need to check the performance for efficiency, no load, losses, regulation, power factor. So once we check the performance, if they are in the normal range, then it is said to be okay. Then tank design. So what is this tank? Inside this tank, we keep the core and the windings. Okay, so this tank is nothing but it is nothing but a container. We need to find the calculated dimensions of this tank: length, width, height. And this tank is also, to this tank there is a cooling tubes are attached. Cooling tubes are attached, and we need to calculate the number of cooling tubes of that one. So the design dimensions of the tank we are getting is: width of the tank 0.6 meter, height of the tank 1.6 meter, temperature. And once we check calculate the dimension of the tank, check the temperature rise, how much it is, okay. uh, the temperature range we calculate is 150 degrees Celsius, but the given temperature is 50 degrees Celsius. To maintain the 50 degrees Celsius, we required a cooling tubes. And how many number of cooling tubes we are required to maintain the temperature in 50 degrees Celsius? It is, we have calculated number of cooling tubes required for this is 96. Number of cooling tubes required is 96. Okay. Now I have framed all the data in this table. Okay. By using these values, we'll start proceeding the drawing of the auto transfer. Drawing of the auto transfer. So I will simply just show you. Tomorrow sessions will see how exactly we are drawn. So if you see the transformer from the top view plan, see the transformer from the top view. So you can see here the circular rings are nothing but a windings. So this, the middle one, is nothing but a yoke. If you see from the top view, this is yoke. You can see this is three-stepped yoke, and the first winding is LV winding, over which we have placed the H winding. Now you can see the diameter of the LV winding, what is the inside diameter, outside diameter of the windings are given here. Okay, so if you see that once we obtain the dimensions of every parts, okay, by using those dimensions we have to draw the transformer. Okay, and if you see the transformer from the top view, that is nothing but a plan. This is how it looks like. This is how it looks like. Now this is nothing but a transformer front elevation. Okay, from front view, how the cross sectional view of a transformer look like. So this is how it will look like. Okay, these are nothing but a, see this first link. This is a core, center link core, okay, and the top and bottom one is nothing but a show. So since it is a three-stepped, so the structure from front it look like this one. Okay, and here is the winding. So first winding is LE winding, over which we have H winding. So you can see this white surface at the top and bottom. These are nothing but a insulation plates over the top and bottom of the windings. So once we obtain this data, we'll draw this transformer top view and the front elevation and tomorrow's session. Okay. So this is all about the design of transformer. So from this table, so while drawing the transformer tomorrow, so we use this table, we use the data from this table and we'll draw the transformer. Okay. Now coming to the design of DC machines. Design of DC machine. Okay. So as we have designed the transformer, the same thing we have to design for DC machine. What are the parts of the DC machine? Uh, uh, Main thing is what? Stator. Stator is nothing but a yoke. Its main poles, field poles, interpoles, field windings. We have to design yoke, main field poles, interpoles. If there are interpoles, then field windings. We have to design these things. Then coming to the armature, that is a rotor, armature body and armature winding. What is the diameter and length of the armature and armature windings? Okay, size of the armature winding. Then in a DC machines, we have also a commutator device that will convert DC to AC. We have to design the commutator also. And there is a brush holders. Brush holders will carry the current from the commutator and it will give to the external load. We have to design the brush holders also. Then bearings. Okay, bearings are placed between a shaft and the rotor. So we have to design the bearings. Then enclosures. Fine. So if you see the DC machines from the front view, it will look like this one. So this part, center part, where there is a slots, you can see there is a slots here. So these slots are used for accommodating the armature winding. So this is armature. Okay, so we have to design armature diameter and length. So this part is nothing but a commutator, and these are the main poles. And between main poles we have a interpoles. So small structure, they say interpoles. Okay, over the main poles we have a field windings. Over the interpoles we have a interpole windings. Okay, and the outer body is nothing but a yoke. Outer body is nothing but a yoke. So we have to design the armature diameter and length, yoke height, width, okay, and what is the air gap, and what is the size of the conductor for field winding, what is the size of the conductor for armature winding. So these are all things we need to design. Okay. Again, firstly, I told you what are the specification of DC machines given. So again, what we need to design the DC machines for these ratings for 250 kilowatt, 400 volt, 625 ampere, 600 RPM, and the windings are used in armature. There are two types: lap winding and wave winding. So here they are told they have to use lap winding. Okay, so the lap winding DC compound generator. They are saying. Uh, and what are the limits of the performance? The peripheral speed of the armature. Okay, armature speed. Okay, uh, per meter. Okay, how much it is. That is 25 meter per second. It should be in the range. Voltage between the commutator segments. It should be 15 volt. Iron losses. It should be a bit greater. It should be equal to 3 kilowatt, less than or equal to 3 kilowatt. It should be less than 3 kilowatt. Then total losses at full load 18 kilowatt. Temperature rise of any part. It should be in the range of 50 degrees Celsius. So by keeping these all things, okay, we need to design a DC machines and obtain the dimensions for armature, poles, armature winding, field winding. Okay, these are the you can see these are the equations. Output equation: d square L equal to 1 by c naught into pa by, yeah. Okay, so d is what diameter of the armature, L is the length of the armature. Again, as we did for transformer, the same thing, but the equations are different. We need to follow those equations, and we need to design the parts of the machines. After designing, check the performance whether the it should be in the normal range or not. If it is a normal range, it is said to be okay. If it is going beyond the normal range, again we need to assume the assumptions and start designing uh, the parts again. Okay. So for DC machine also we have designed. Okay. Uh, uh, what we do quickly, we'll see the table. Since there is a less time, tomorrow we need to draw this both structure transformer and DC machines. So quickly we'll see this table. So we have table after designing the DC machine. Okay, so these are the dimensions we obtained: armature diameter, armature gross length, number of poles, how many. Okay, so again by using this table in tomorrow's class or in tomorrow's session, okay, we'll draw the structure of the DC machine. For DC machines, we'll only draw the front elevation, front view. Okay, not top view, front view, cross sectional view. Okay. Now these are what we have designed the electrical machine. Okay, and we have checked the performance. Okay. Now what this is what manually we did. Okay. Now see. Now we'll see computer aided design and drafting. So that is CADD. Okay, what is computer design and drafting? So we have a CAD for designing, we have a CAD for drafting. So what is CAD? Computer aided design. Okay, so far what we have designed for transformer and DC machine, that is manually by hand we have designed. Okay, but we want to design these things by using computers, by using programs. That is nothing but CAD, computer aided design. So it is a method by which electrical machines are designed with the use of programming in C++, Visual Basics, Java, MATLAB, etc. So what we do, we write a program for designing the transformer, for designing the DC machines, by taking all the input specifications, by assuming all these things, by giving all the equations. Okay, we write the code for design of a transformer. Okay, once the code is written, it should be in C++, Visual Basics, Java, or it should be in MATLAB. Next thing is what? Once the code is written, execute that one. Once it is written, simply is what? Feeding the input data, okay, and will check the output dimensions and performance. Simply, that is nothing but a computer aided design. And we use the tools like MATLAB, Java, Basics, Java, Visual Basics, C++, or many things are there. Even nowadays, even the software is also there for design of a transformer, decimal. Just thing is what? Simply we need to feed the inputs and get the results. Okay, results means what? Output, dimensions of the various parts. Okay, so to make those softwares, we need to write the programs, we need to write the codes, and to write the codes or programs we should have the knowledge of design of a transformer, various equations, what are the assumptions we need to make. So once we have the knowledge of these things, we will write the programs. Okay, we'll make the softwares and all that. Okay, there is a MATLAB for that one also. This is nothing but a computer aided design. Now, computer aided drafting. What is computer aided drafting? Okay, so this is the next phase of the design process, which is done by using computer aided programs to create drawings. So what one CAD is what? That is computer aided design. Okay, One CAD is what? Computer aided drafting. Drafting means what? For drawing. So once the design process is over, once we obtain the result from the computer aided design, by using those uh, the output results, okay, we start computer drafting, that is drawing by using the computer programs. And the one best tool in CAD is, that is computer drafting, is AutoCAD. So this is a command software application for 2D and 3D computer aided drawing. Okay, for computer aided drafting, so we use AutoCAD as a tool. We use AutoCAD as a tool. So how this computer design is done? These are the key benefits of a CAD. So decrease in error percentage. Okay, compared to the manual by hand drawing or hand designing. Okay, what are the benefits of the CAD? Decrease in error percentage, decrease in effort, saves time, easy to edit. Okay, code reuse, improved accuracy, easy to shape. So for all these benefits, we go for CAD, that is computer design, designing of the transformer, the designing of the electrical machines, and we go for drawing of these structures using CAD tools. And here the CAD tool for drawing the structures we are using is AutoCAD. Okay. And what is the design procedure in computer design? Okay, this is one example I have shown, that is general example for electrical machines. That is a flow chart. Okay, first thing is what? Specifications. Then based on the specification, choose the materials, matting materials, connecting materials, insulating materials. Then assume the design parameters like specific loadings. Okay, current loadings, etc. Assume these things. Okay. Next thing is what? Design process. Magnetic circuits, electrical circuit, mechanical, thermal designs. Okay. Then after doing all these things, performance calculation. Is performance satisfactory? Yes. Print the design sheet. This is how we start the coding of the electrical machines. Okay. If this performance is not satisfactory, modify the assumptions. Again, start the design process. Okay. Once the performance is satisfactory, print a design data sheet. Okay. This is what flowchart for creating the program for design of electrical machines. Then computer design of transformer. This is a flowchart for design of computer of design of a transformer. The same thing is specification, constraints, okay, starting point, okay, specify maximum and minimum limits of design parameters. Okay, what is the maximum temperature limit, minimum temperature limit, maximum losses, specify those things. Okay, then choose proper values of design parameters, assumptions, specific loadings, magnetic loadings, space factors, and all that. Assume those things. Then design magnetic frame, LV winding, HV winding, then performance check, calculation of iron losses and copper losses, calculation of efficiency, reactance, regulations. If all thing is okay, further process for cooling system design. If everything is okay, print the design data sheet. This is what a flow chart for computer design of a transformer. So using this base of a flow chart, we can create the code for design of a transformer. And rotating machines are same things. Okay, specifications are given. Choose the assumptions, calculate dimensions for different parts, stator, core, yoke, and all that. If it is satisfactory, performance satisfactory, print the sheet. If it is not, go again, redesign the dimension. That is computer aided design of rotating electrical machines. Okay, so this is what. Next is what, see here, for AutoCAD installation. So once we have designed this transformer, from the design output, we draw the drawings, okay, in AutoCAD. So this is the okay. So what, this is the AutoCAD software. So I have installed 2016 AutoCAD software. Okay. So this is how it looks like. And what is the procedure for installation? See here. Wait a minute. So while coming to tomorrow's session, uh, install this AutoCAD software. There is a many versions of AutoCAD software. I have installed 2016. So you can see this PDF, right? So here there is a steps for creating the downloading the AutoCAD from the Autodesk website and install that one. So you can see what is the step. So go to the site studentsautodesc.com. Okay, once you go to that site, okay, you have to create an account, okay, by using your better if you have your college mail IDs, that will be better. If you have the college mail IDs, you can install the free trial for 1 year or maybe 3 years if you have the college IDs. Okay, so you have to create the account with your college ID. Okay, then click in sign in. See, this page will open. Okay, now what? See, I will share this PDF in that WhatsApp group. Okay, here they are shown for the download of uh, Revit software. So same procedure is followed for AutoCAD. See, so you have to download AutoCAD software, not Revit. Revit is for mechanical things. Here this PDF is for Revit software. Okay, so you have to install AutoCAD. For they are shown for Revit, but it is same procedure for AutoCAD also. Okay, to follow these steps, I'll post this PDF in the Google class in the WhatsApp group. So follow these steps. So if you have your college ID, college mail ID, so you can install this for 1 year free trial. Okay, or else what you do, there is also we can install the AutoCAD for 30 days trial, and for 30 days trial this is the link. So once you open this link, okay, here we have to choose a free trial, and in this free trial we are downloading the AutoCAD. Select AutoCAD. Okay, and here we have to select as a student or teacher, then create the account. Once you create the account, you will get a mail. So verify that uh, mail. Okay, once verified, we have to fill the education details, then continue. Then which software you want to install, select that one. There is a 2016, 17, 20. Okay, so you want 2019 or anything, select that one, 64-bit English, download it. Okay, and install it. So these files I'm posting in a WhatsApp group. Follow these steps. So next session, okay, so learn some basics things we learn some basic things in AutoCAD. After learning the basic things, we start drawing the uh, structure of a transformer. For the data we have obtained from that table, we use those data and we'll start drawing the transformer. Okay, simply I have drawn. So you can see here. So this design, this drawing of a transformer will draw in uh, next tomorrow session. Okay, so before that one you should know. So once you install the AutoCAD software, okay, I installed 2016. Okay, open that one. So what are the things are there in AutoCAD? Okay, so first thing is what, we'll set a new page. So once you open the page, first thing is what? Okay, just simply type units. Okay, now click units. Okay, now set. So here we are creating the drawing of transformer or DC machines in dimensions in millimeters. So for that, you set this is to decimal precision, how much precision you want after decimal point. You set that one for angle. So here it is in inches. Set this to millimeters. Okay, okay. Set this to millimeters. So once you open the software, the first thing is what set the units. Okay, so first this page will get open here. So from this page, okay, you have to select the templates. From this template, take ACAD.dwt, select this one, open this one. Okay, once you open this one, set the units. Just type units, enter. Okay, and keep this in millimeters, and okay, okay, and okay. And here you can see there are the commands. From these commands we can create the drawing, we can draw the drawing. Here line command is there, polyline command is there, circle is there, arc is there. Okay, and you can see here we have a special commands like move the object, mirror the object, copy the object. We have special command. Where there is one more command, that is a text command. From this text command we can write anything on the drawing. Okay, and this is a dimension check. Okay, dimension check, what if I draw the object. Okay, what is the size of the object, so check that one, so specify that one. We use the dimension command. Okay, uh, next is what you can see here, display drawing grid on. If you click this one, you can see if it is off. So click the grid on, will get a graph at the background. And this is what snap mode on. Okay, snap mode on means what? See, if you place a cursor, it will always jump to the points of on that graph. Okay, see on that graph. If it is off, it will not jump to the points. We can place the point anywhere. So if this is on, so it will jump to the points on that graph only. Okay. Now this is what? This is ortho. Ortho mode on, off. What is this ortho mode? See here. I'll select a line command. Okay. I'll place first point. Click the first point. Okay. Now stretch it. If ortho is on, we can draw this line in a horizontal way or in a vertical way. Okay, exactly 90 degrees or 180 degrees line we can draw if the ortho is on. If the ortho is off, I'm making the ortho off. So we can draw the line with any angle. We can draw the line with any angle. So this is what. If ortho is on, we can draw the line. So to draw the line, select the line command, specify first point, and in which direction you want to draw the line. Take the cursor that direction. If you have the dimension of the line, just simply type the value. Just simply type the value. Now I'm typing the value like 1000 mm. So 1000 mm is correct. I think unit 30 units to millimeters only. Okay. I'll type the line 400. So whatever the value you can type, it will set. Just type 10. So this is 10. Okay. If you want again 10, and 10. So this is how we use the line command. Line, simply specify first point, second point, at what distance you want, specify that one. If it is 9, specify 9. Simply enter the number, type the number, and enter it. Okay, and continue. If you don't want if you don't want to continue again, press enter. It will stop the line. Okay, click the line. First point, specify the distance. Second point, click. Okay, the line is continuing. Then again press enter. Okay, this is how we use the line command. So polyline is what's here. What is the difference between line and polyline? Line is what, see, if you want to delete this part only, so that is done by with the help of drawing the object from the line command. We can delete this one. So how to delete this one? Left click, select this one, and delete option. Left click, delete option. Or click here, the box, cover the object, and click left click and delete. Okay. Now polyline. The polyline is what? Enter. Now, if you select the object, all lines will get selected. Okay, but in case of line, okay, so particular point of line only gets selected. But in polyline, whole object will get selected. So we can delete that one. This is the difference between polyline. So always we use a line command only. Polyline rare we use. So line command is we use for drawing the drawings. Okay. Now circle. How to draw the circle? Uh, we have to draw the circle. We have different methods. Circle with the radius, circle with the diameter, 2 point, 3 point, and all that. So maximum we use circle with radius and diameter. With radius, click the circle with radius. Specify first point. Okay. Then what radius of the circle we want? Specify that one. 5. Okay. This is 5 mm radius. Okay. Now if you want a circle with diameter, this is circle with diameter. Okay, this is how we draw the circle. Okay. Now coming to the arc. Okay, we have a arc, 3 point arc, start, center arc. How to draw this arc? Okay, and to draw this arc we required 3 point. Okay, select arc, maximum we use 3 point only. First point, make ortho off for this one. Second point and third point. Enter. This is how we draw the arc. Okay, how to draw the 3 point arc? Select 3 point arc, specify first point. So in many drawings we always get the first point, third point, and last point. So by using those points, we can draw the arc. So here simply randomly we choose the first point and second point. So this is how we draw the arc, 3 point arc. So there is a start, start, center, and so maximum we use 3 point arc only. Okay. So these are the commands from which we can draw the object. Okay, we can draw the object. Okay. Now see, this is ortho, and what is this one? Rested cursor to specific angles. So you see, if ortho is on, the cursor will move to 90 and 180 degrees. Okay. Here also we can set to 45 degrees, 90 degrees, 35 degrees, or 30, 60. By selecting this one, we can set the cursor. I can here chosen to the 30 degrees. I can set to 30 degrees. So it will get stuck to 30 degrees anyway. We can draw the line at 30 degrees. Okay. Now, I will make this off. See, I want to draw a line, okay, at particular angle. Okay, I want to draw a line at 45-degree angle. So for this, what? Press tab. So if you press tab, it will come to the angle box. Here you can specify the angle. So I want to draw a line of 45 degree. Specify 45 degree. Then again go to tab. Okay. So this line is get stuck to 45 degrees. So if you want a line at 45 degrees, specify that line length. Maybe 20. enter. So how to give the angle for a line here? First point, okay. Now I want to draw a line at 60 degrees. Tab, press tab, will come to the degree angle box. So draw if you want a line at 60 degrees. At 60 degrees, again press tab. So it will go to the uh, line dimension box here. So there you can specify the dimension of the line, length of the line or anything. Maybe 10. So with the help, see, this is how we use the angle to set the angle of the line. So with the help of the scroll from the mouse, okay, so we can zoom it or zoom in or zoom out. Okay, zoom in or zoom out. Fine. And if you press the scroll, you can move the drawing in any position. Okay, you can move the drawing in any position. Fine. So now this is what, see, there is also a rectangular is there. So from this we can create a rectangle box. Okay. Take a rectangle box, specify the dimensions. So here at this, uh, the here we can select a dimension. Okay, specify length of a rectangular like 10. Enter. Then width as 5. Enter. So we can draw the rectangle like this. Okay, you can draw the rectangle like this. Fine. Uh, so these are all line, circle, arc command. Now the special commands. Now special commands. See, uh, first I will delete all these things. Delete. Okay. I will draw a circle. Now move. I want to move the circle from one place to other place. I want to move the circle to the right side. So choose move command, select the object, press enter, choose any base point. Choose any base point. Okay. I'm choosing the center base point. So from center base point, I can place this circle anywhere. Okay, this is the move command. How to use the move command? Select move command, select object, enter, specify the base point from which we can move the circles. Okay, so this is the move command. Next is copy. Select copy command, select the object, same procedure, enter, choose the base point. I'm choosing as the center as the base point, so I can copy many objects of this circle. Enter. Okay. So control Z. If you do the control Z, it will do undo. The control Z is undo. Fine. How to move the how to copy the circle? Select the object, enter, to the base point from which you can move the circle. Okay, from which you can move the circle. Enter. Okay. Uh, so on. So there is a line. I want to place a circle at center of this line. Okay. So how to do that one? Copy, select, enter. To place a circle at the center of the line, you have to choose the base point at the center. Then move. Ortho, off. Now you can get a point. See, the software will show the center point also. Okay. Click there, enter. So place a circle at the center of the line. See here, when you select a line command, it will always showing the points here. Okay, always show the midpoint, end point. How these points are showing here? See here, this command. See, snap pressure 2D. Here, if we have to select end point, midpoint, center, node, or anything. So don't select these things. Okay. Now see, if you If you draw a line from this point, it will not show the point here. Okay, and to show the exact point, okay, we should always make this on. Always make this on. Okay, when you make this on, it is showing the points from this point. Enter. See, if you press again enter, again it will start the line command. So previously which command we are using, if you enter that one, it will start the previous command. Okay, if your previous command we have chosen like uh, circle, so place the circle, enter. Again if you press enter, it will again select the circle. Okay, so we are done line command, circle, arc, rectangle, move and copy we did, rotate. Okay, so just draw the one rectangle. Now I want to rotate this rectangle. Okay, there is a rotate command. Rotate, select the object, enter. By which point you are rotating the object, select that point. Okay, by which angle you are rotating the object here. Okay, you can specify that one also. If you want to specify, if you want to rotate the object at like 45 degrees, and put it order to 45 degrees. Okay, so rotate, select, enter, base point, enter, and rotate the object. This is rotate command. Mirror, select mirror command, select object, enter. At which point you want to mirror of this object. Okay, see, click here, it will get placed. So mirror of the object is formed. Okay, how to use the mirror command? Mirror, select whole object, enter. I'll specify point here. And this is how mirror is formed. Okay, this is mirror command. Next, now trim. Now see here. Trim is what? Trim is what? See, to remove the unwanted dimensions, unwanted lines of anything. So trim, select trim. Once you select the trim, press enter. Okay, press enter. So I want to delete this line. Select this line. I want to delete this line. Select this. And let's see if see trim. Select trim. Before only press enter, I want to delete this point and delete this point. Fine. Enter. This is how we use the trim command. This is how we use the trim command. Fine. Next is offset. Okay. Now how the offset is used? See, there is a one line. Okay. I want the same line at the right side at a distance of something. For example, I want this same line at a distance of 5 mm. Select offset, specify the distance 5, enter, select object. Which side you want to place the object? Move the cursor mouse that side and click. Again select, you want multiple object, click to right side. Select the object, click at the right side. If you want the same over the left side, select the object, click at the left side. Select the object, click at the left side. Select the object, click at the left side. This is how offset command works. Okay. Now coming to text. Okay. So if you want to mention anything, any information on the drawing, select multi-line text. Okay. First point, enter. Okay. Now you can type anything. Okay. It is AutoCAD. No, we want to increase the font of this guy. This one, select here, press to 2, enter. Okay. Again, if you don't want the font of this AutoCAD less than this one, select this AutoCAD, right click, go to text edit. Okay, select the text. Here we can change the font. So I'm changing font to 1. Enter. Now click outside. So this is how we use text command. This is how we use the text command. Fine. Now coming to dimensions. See, there is one line. I want to mention the dimension of this line, length of the line or anything. Here, there is a linear. Choose linear. Specify first point, last point. Enter. Now you can see the dimension of the line as 7 mm. 7 mm. If you want to increase the text of this dimension or arrow mark of the dimensions, so here go to annotation. Okay, go to standards. Now manage dimension style. New one. You can name it. Continue. Okay, and now go to symbols and arrows. So here you can set the size of the arrow. Okay, so I'm setting size of the arrow as zero point 0.5. Okay, now text. I'm setting size height of the text as 1.5. Okay, now okay, close. Now select this dimension, right click. Okay, now dimension style as, yeah, now you can see we have increased the text font and arrows. Okay. Now how to mention the dimension here? Select linear, select point, first point, end point, and move the cursor, move the mouse. Okay, if there is a circle of radius, okay, I want to mention the radius of the circle. Go here, choose circle with radius, simply select the object. Let's see, this is a circle with radius 3.9. If you want to mention the diameter of the circle, go to diameter, select the circle. So this will mention diameter of the circle. Okay, this is how we use the dimension, linear and mentioning the radius and diameter of the circle. Okay, so these are the commands: line, polyline, circle, are drawing the drawings, and these are the commands, special commands like move, copy, and all that. Okay, here these are the settings. Ortho means what? We can draw the lines horizontally, vertically. Hmm. So this is what snap. If you off this one, we don't get the exact points for drawing the object here. So always keep this on. Okay. So in WhatsApp group, I'm posting that steps to download and install the AutoCAD software. Okay. So you can also install this AutoCAD for 1 month trial if you have your Gmail mail ID, or if you have your college mail ID, institution mail ID, you can install this for 1 year. Okay. So in tomorrow's session, uh, we'll draw the drawing of a transformer and the DC machine. This one. Okay. So we'll only draw the top view, that is a plan and front elevation. Same drawing how we have drawn. I will explain. I will tell you in the tomorrow session. And DC machine. So DC machines, the same thing. We'll see. DC machines how to draw the armature, poles, yoke, and all that. So in tomorrow session, we'll learn about the drawing of transformer and drawing of DC machine. Okay. Uh, Bhargav, Bhargav, are you there? Bhargav, are you there?
He has some network issues, sir. He'll be back in a moment.
Okay, fine. So we are done with the today's session, and tomorrow we'll look after drawing of a transformer and the DC machine. So, students, you have any questions, any queries for the today's session? Does anyone have any questions? Yes, who is there? Bhargav, are you there? Bhargav Sai.
Yes, sir. Thank you for the session. If the participants have any doubts or queries, please post the queries in the chat box or turn on your mic to ask them.
So Bhargav, what I'm doing, I'll post a PDF file that is regarding the installation guide for the AutoCAD in the WhatsApp group. Okay, so by coming to tomorrow's sessions, please install that AutoCAD software. So we'll learn how to draw the transformer and DC machine in tomorrow's session. So before coming to the next sessions, please install the AutoCAD software of any version, 17, 18 or 19. Okay, and the guide for that one I'm posting in the WhatsApp group. Okay, so anybody have any queries,
Okay, sir.
questions? Okay, Bhargav, then
Okay, sir. So we put an
we'll wind up the today's session.
yes, sir. Thank you, sir, for an amazing session today. We learned quite a lot of new things. I thank all the participants for joining in again. We are looking forward to having you all in our second session tomorrow at the same time with the same meeting link. Thank you all.
Arun T. Okay, fine. Bhargav, I'm sending you the PPT. If you have all the participant mail IDs, you can forward the PPT to them. Okay. So some of the participants are asking PPT of this session. So I'm forwarding you the PPT, Bhargav. Okay. So you can mail those people that PPT to all the participants. Fine.
Okay, sir, we will.
Okay.
Thank
Fine.
yes, sir. Fine.
Okay. Okay. Fine.
Thank you for all the joining the session.
Okay, thank you for all. We'll meet in the tomorrow session. Thank you.